Day 3 of 365 stayed with complexity analysis, but from the memory side instead of the runtime side. That mattered because a solution can be fast enough and still be the wrong answer if it burns too much memory. The useful shift today was treating space complexity as a first-class part of algorithm quality. It tells me how memory usage grows as input grows, and that becomes a real constraint much earlier than people expect. The first big lesson was that space complexity is not about counting every local variable in a function. A few counters or pointers do not change the class of the algorithm. What matters is whether the memory growth changes with input size. If the algorithm creates another array of size n, that is O, n, extra space. If it keeps only a few variables no matter how large the input becomes, that is O, 1, auxiliary space. Another useful shift was separating total space from auxiliary space. Total space includes the input and everything else the algorithm uses. Auxiliary space focuses only on the extra memory beyond the input. That distinction matters because the input is usually given. What I really want to understand is how much extra memory my solution adds on top of what already exists. That is usually the more useful interview metric. The most practical lesson today was that recursion has a hidden memory cost. Even when the code looks short and elegant, every recursive call adds a stack frame. That frame holds local state, return information, and the point where execution should resume. So a recursive algorithm can use O, n, extra stack space even if it never allocates another array or hash map. The memory cost is still there. It is just implicit instead of explicit. That is why recursion feels different once space complexity is part of the analysis. Two solutions can have the same runtime and still behave differently in memory. An iterative version may stay at constant auxiliary space, while a recursive version grows with the call depth. That does not make recursion wrong. It just means the trade-off needs to be visible when the constraints are tight. Another useful shift was understanding what in-place algorithms really mean. In-place does not mean zero memory. It means the algorithm avoids allocating extra memory that grows with the input size. If I reverse an array by swapping elements inside the same array, I can do the work with constant auxiliary space. That is different from building a second array of the same size, which would push the extra space to O, n. That also clarified why in-place work is a trade-off and not an automatic win. Tighter memory use is great, but mutation can make code harder to reason about or can violate other constraints in the problem. Sometimes the cleaner answer uses more memory and is still worth it. Sometimes memory pressure is the whole reason to choose the in-place approach. Space complexity gives me the frame for making that trade-off explicitly. This topic matters outside interviews too. Production systems often fail on memory pressure long before they hit theoretical runtime limits. Maybe a service duplicates large payloads in memory. Maybe a recursive workflow grows the stack too deep. Maybe an algorithm builds temporary structures that scale badly with the request size. Thinking about memory growth early helps prevent those problems instead of discovering them after load increases. Another thing Day 3 improved was how I read solutions during review. I do not want to ask only whether the code is fast. I also want to ask whether it copies data, whether it can work in place, and whether recursion is hiding a cost that the surface code does not show. That makes the analysis more complete, especially when two solutions look similar at first glance. So my main takeaway from Day 3 was that space complexity deserves the same attention as runtime. Ask how memory grows. Ask what extra memory is truly auxiliary, and ask whether recursion or copying is the real hidden cost. If those questions become automatic, later topics like trees, graph traversal, backtracking, and dynamic programming become much easier to judge. That is what made today useful. Memory stopped being an afterthought and became part of the design lens.